Today's lesson, stoichiometry in solutions. If you know the atoms or ions in a formula or reaction, you can use stoichiometry to determine the amounts of these atoms or ions that react. If a precipitate forms, the net ionic equation, we talked about the net ionic equation last class, right, where we dissociate the ions, right, and then we cross them out, and the ones that we're left with that form the precipitate are the ones that are actually left over, and that's what the net ionic equation is. And that's the equation you're better off to use if that's the only part that you're actually going to use. So we've got to, we're recapping now all the stoichiometry stuff. Remember, first thing in stoichiometry, what's the first thing you want to do? Equation. Start off with your chemical equation. So it's really important, guys. Again, I can't reiterate it enough. Make sure you know your polyatomics. Make sure you know how to put together your formulas. Like I said, you mess that up, you mess up the entire question. Sample problem. Calculate the concentration in moles per liter of chloride ions in each solution. So what we're going to do is, in part A, we're going to start off with 19.8 grams of potassium chloride is dissolved in 100 milliliters of solution. So it's going to dissociate into the following. KCl, right, is going to break apart into potassium ions and chloride ions. So what we've got is 19.8 grams of potassium chloride. So what we want to do is, because we're going to be using stoichiometric methods, from this equation we want to start off with trying to find the number of moles of potassium chloride. To do that, we want to take our mass and we're going to divide it by the molar mass of potassium chloride, which is 74.55 grams per mole. Grams cancel out, and we're left with 0.266 moles. Now, we've got 0.266 moles of potassium chloride, 0.266 moles. Question asked, calculate the concentration of the chloride ions. Concentration is in moles per liter. What we want to do is we want to find the number of moles of our chloride ion, X. So using stoichiometric methods, right? Remember what we were doing? We were trying to find the number of moles and old-fashioned way of molecules. Even though we know about the Avogadro constant, we're treating molecules the old-fashioned way. By using the coefficients that are in front. So, our unknown number of moles that we're trying to find of is for the chloride ion, the Cl negative. Now, what's our given? Our given is potassium chloride, which is 0.266 moles. We are, in this reaction, the ratio is a 1-to-1 ratio. So because it's a 1-to-1 ratio, whatever the moles are for our given is going to equal the moles of our unknown, right? So because it's 1-to-1, the Cl, the number of moles of Cl negative is equivalent to the number of moles of our potassium chloride. So therefore, the N value, okay, of the chloride is equal to 0.266 moles. Now, we're being asked to calculate the concentration. Concentration, the equation for the concentration is C is equal to N over V. So what we're given the N value here, 0.266 moles. We're being asked to find C, right, concentration. We need to find our V, right? And our V should be given, and our V is given. Our V is 100 milliliters. But if you look at the units, right, let me just uncover the units. It's moles per liter. So I must convert 100 milliliters into liters, which is 0.100 liters. Now, for argument's sake, I'm going to convert 100 milliliters into 100.0 milliliters, just to avoid the one significant digit rule for my answers, because I hate those type of questions. where the answer kind of rounds off to 1. So what we're going to do, and I don't want to go into an explanation of why we don't really use those as the number of significant digits. But anyway, we've got our volume, which is 0.100 liters. Concentration, what we're finding, we've got the number of moles. Right? So to find the concentration, we're going to divide our N value, which is 0.266 moles, and we're going to divide it by our volume, which is 0.100 liters, and the concentration of the following is 2.66 moles per liter. So least number of significant digits are 3, so our answer is going to have 3 significant digits. Remember, I've changed the 100 milliliters into 100.0 milliliters just for some better significant digits. So keep this question, the answer for this one in mind, because we are going to need this, some of the numbers in this question, right, for part C. So let's look at the next sample problem. The next problem, same thing. We're calculating the concentration of the chloride ions in each solution. We have 26.5 grams of calcium chloride dissolved in 150 milliliters of solution. So again, let's make an adjustment to this one. Instead of 150 milliliters, 150.0 milliliters. So first thing, you want to start off with your equation. So our question starts off with 26.5 grams of calcium chloride. So we want to convert our mass into the number of moles. To do that, we're going to take this value and we're going to divide it by its molar mass. And its molar mass is 110.98 grams per mole. So grams cancel out, and I'm left with 0.239 moles. So of calcium chloride, I have 0.239 moles. Right? According to our stoichiometry problems, we're trying to find out the concentration of the chloride ions. So this is what we're trying to find. And with the example before, it was a 1-to-1 ratio. But now it's a 1-to-2 ratio. Right? We look at the coefficients. The coefficient here, there's no number, so it's 1, right? It's a 1-to-2 ratio. So what we do is, so we're revisiting our stoichiometry. We have our unknown, which is the chloride ions, and our known, which is our calcium chloride. So we know how many moles, right? We have moles and molecules. Right? And as I said, molecules, even though we know now the Avogadro constant, we're not going to treat it that way. We're going to treat it the old-fashioned way in terms of molecules. Okay? So we've got, we've just calculated 0.239 moles. We're trying to find the number of moles of chloride. We have how many molecules of chloride? 2. How many molecules of calcium chloride? 1. Right? So now, remember, let's just recap the stoichiometry. Right? We separate the two columns with an equal sign. Right? So we have x over 0.239 equals 2 over 1. And what we're trying to find with this x is we're trying to find the number of moles of the chloride ion. So we're left with x is equal to, and all we're doing is shifting the 0.239 over the equal sign. And we're given 2 times 0.239 over 1, which isn't really going to matter. Right? And our answer comes out to 0.478 moles of the Cl negative, right? The chloride ion. So we know the number of moles of the chloride ion. And again, now we want to find, though, the concentration. right? So look at what we're asked. We're asked to find the concentration. It's in moles per liter. We've already found the moles, which means now we need the liters. Do we have the volume?
Yeah.
Yes, so we can use the equation. C is equal to N over V. N, our number of moles that we've just calculated, 0.478 moles, divided by 150.0 milliliters, which is equal to 0.1500 liters, right? We want to keep the same number of significant digits. Right? So if you're converting a number, keep the same number of significant digits. Right? So 0.478 moles divided by 0.1500 liters is equal to 3.19 moles per liter. So that is the concentration of the chloride ions. So we have this answer, we have the other answer. So now let's go about solving sample problem letter C. Sample problem letter C says to calculate the concentration. Now the mixture of the two solutions in part A and B, assuming that the volumes are additive. Right? We're going to combine them. Right? So let's look at the total combination of moles. Well, if we look at the total amount of Cl that we've collected, well, in terms of in moles, okay, we had 0.266 plus 0.478. So what we're doing is we're taking our answer from, all the number of moles from question A, and we're adding it to the number of moles from question B. And we get a total number of moles, which is 0.744 moles. Now, what we want to do is, we're trying to find, again, concentrations. We're trying to find now the volume, right? So the volume of the chloride. And all we're doing is we're adding the volumes of question A with the volumes of question B. And we get 0.250 liters. So we've got our N. So here's concentration, N over V. So we've got our N, additive, right? Combined. We're combining the number of moles that we've found. We're combining the amount of volume between the two questions. We're adding the two together, and we're just throwing that into our equation. So we get 0.744 moles divided by 0.250 liters. Give us a final answer of 2.98 moles per liter. So we're going to keep it to 3 significant digits because that was the least number of significant digits in our question. Okay. Next sample problem. The leaves of a rhubarb plant contain a high concentration of oxalate ions, C2O4-2, which is in fact very poisonous. To determine the percent of oxalate ions, a student measured the mass of some leaves. The student grounds up the leaves and added excess calcium chloride solution to precipitate calcium oxalate. The student tested 238.6 grams of the leaves. Now, the dried mass of the calcium oxalate from the leaves was 0.556 grams. What was the mass percent of oxalate ions in the leaves? Now we're looking at it and going, oh my goodness, this is a really long question. Right? So where do we start? Where do we always start? Formula, right? Our actual chemical equation. So let's start off with the chemical equation. I'll give it to you guys just so you guys can kind of, know where we're going. So all we're looking at is we're trying to find the oxalate ion. Right? We formed the calcium oxalate in our question. So now we've got our equation, and so all we've got is a dissociation of the ions. So we've got calcium ions, the oxalate ion, right, in aqueous solutions, and it forms a solid calcium oxalate. So now, using that, take the information and go about trying to devise a plan to solve the following problem. Now, one of the questions says we've added it in excess calcium chloride. Right? So what we've got is we've got this double displacement reaction, and the only part we've kept were the parts that helped form the precipitate. So we didn't care about the rest of the equation, right? Because it's only going to make things a little more complicated. So we've only, this is the part that I kind of stated at the beginning, where it says you're better off, if you've got certain precipitate equations, you're better off using the net ionic equation. Now in this question, right, we form the precipitate, which is the calcium oxalate. Right? That's that. So all we care about, even though we're adding excess, right, we know that we're adding all this extra calcium chloride to get this reaction. But all we're trying to do is we're trying to collect the actual precipitate. So we've collected this much of precipitate. So what we want to do is we want to find out the amount of the oxalate that's actually going to be used to end up forming this precipitate. So what do we have in terms of numbers for this question is, well, we've collected 0.556 grams of that. So we've got our mass, and always in terms of stoichiometric problems, what we want to do is we want to take the mass, right, of this, the calcium oxalate. So what we want to do is we want to find, right, the molar mass of calcium oxalate. And we're going to divide the two together. And the molar mass is 128.1 grams per mole. So grams cancel out, and we're left with 0.00434 moles. So we've got 0.0043 moles of the calcium oxalate. So our unknown is the oxalate ion. So C2O4 -2. Our given is the calcium oxalate. And we've calculated the number of moles and molecules. So we've got 0.00434 moles. We're trying to find the number of moles of the oxalate, but the ratio is 1 to 1. Because the ratio is 1 to 1, exactly, x is equal to the same thing. So the x of the oxalate is equal to the same number of moles as we've calculated for the calcium oxalate. Oops, moles. Now, we've got the number of moles for our calcium oxalate. Question asks now, we've got 238.6 grams of leaves that were actually being used, right? But this is the number of moles of the oxalate ion. So in order for us to find out how much of it is in terms of a mass, what do I have to find? The molar mass, right? So I find the molar mass of the oxalate ion. Now, the fact that we've got this -2 does not affect calculating the molar mass. Because the molar mass is, right, just the regular, the mass of 2 carbons, 4 oxygens, as normal, right? So when we have the number of moles to find the actual mass of it, we multiply it by the molar mass, and the molar mass is 88.02 grams per mole. Moles cancel out, and I'm given the mass is 0.556 0.382 grams. So we've got 0.382 grams of the oxalate ion. Now, question asks, what is the mass percent? Okay, what is the mass percent of the oxalate ions in the leaves? So, what was the mass that we've collected of the oxalate? 0.382 grams we've collected. What were the mass of the leaves?
238.
Exactly. That's our entire sample, right? 238.6 grams. So we're taking what we've collected of the ion that we need, we divide it by the entire mass of the sample, right? We take those two numbers, we multiply it by 100 to get a percent, and the percent comes out to 0. At least number of significant digits in our question 3, so the answer is 0.160%. So, the mass percent of the oxalate ions in the leaves is 0.160%. So you see now, in terms of stoichiometry, how stoichiometry works, even though we're not looking at, we're actually looking at ions instead. Right? So stoichiometry is going to be a big part because we're actually going to be using stoichiometry. We're going to continue to be looking at it in the coming units. So please don't forget these methods. Right? So they all work the same way. So we've calculated the number of moles. Right? We've been given this amount, this mass, 0.556 grams of our precipitate. So using that, we can actually figure out the number of moles of our ion. And then take that, use the molar mass of the ion to actually find the actual amount of the mass. Next sample problem. Aqueous solutions that contain silver ions are usually treated with chloride ions to recover silver chloride. What is the minimum volume of 0.25 moles per liter of magnesium chloride needed to precipitate all of the silver ions in 60 milliliters of 0.30 moles per liter of silver nitrate? Assume that the silver chloride is completely insoluble in water. So that's going to be our precipitate that we're going to form. Now, one change that I do want to make to this question is we're going to get rid of the 60 milliliters and we're going to change it to 60.0 milliliters. Here is the starting equation, just in case you're struggling to put together the actual formulas. So we've got magnesium chloride plus 2 silver nitrate to produce 2 silver chlorides and 1 magnesium nitrate. We've got 60.0 milliliters of 0.30 moles per liter of silver nitrate. That's this one right here. So what we can do is use that, right? We use that to actually find the number of moles that we have of the silver nitrate. So, of the silver nitrate, we've got 0.0600 liters, right? And we're going to multiply that by 0.30 moles per liter. Right? Liters cancel out. My answer is in moles. So I've got 0.018 moles of silver nitrate. So I've got 0.018 moles. Now, we're trying to find what is the minimum volume of magnesium chloride. What are the minimum moles? The minimum volume of magnesium chloride that we need in order to precipitate all the silver ions. So, what we're trying to do is, that's our x. That's our unknown. So, using stoichiometry, right, our unknown is NgCl2. Right? That's the number of moles X. We've got molecules. We've got silver nitrate, which is 0.018 moles. Now, in terms of the ratio, we have 1 magnesium chloride to 2 silver nitrates. So we can use this to help us find the number of moles of magnesium chloride that will actually be used in this reaction. So to find magnesium chloride again, we've got X over 0.018 equals 1 over 2. So we're going to bring the 0.0818 over, and we're going to get X is equal to 1 times 0.018 divided by 2 to give us the number of moles of magnesium chloride, which is 0.0090 moles. So that is the number of moles of magnesium chloride that we're going to use in this reaction. Right? So we know we're going to use that much. Remember, it's the limiting reactant, right? It's the least number of moles in our question. But it doesn't really matter. Right? But we know that we're going to have to use the entire amount because that's the least amount, and we know that's going to run out. That the minute this runs out, the reaction stops. Right? We're always looking at it in terms of the least number of moles for our reactant. So we're going to take the number of moles that we have here, right? So that is our N value is 0.0090 moles. We've got a concentration, right? We've got a concentration of the magnesium chloride, which is 0.25 moles per liter. We're being asked the minimum volume that we're going to make. Right? So the volume, that's our unknown. And according to the equation, C is equal to N over V. Or if we look at it in terms of the pyramid, C, N, and V, we're trying to find V. So we cover up V, and it's the number of moles divided by the concentration. So volume is equal to N over C. Our N value, 0.0090 moles divided by 0.25 moles per liter. Moles cancel out, and our answer comes out to 0.036 liters. But if we're looking at a measurement, right, if we're trying to put that in a graduated cylinder, right, we want to convert that to milliliters. I'm not going to matter, okay? I'm not going to mind if you don't put that on a test or even in an assignment to convert it to this, right? But think about it in terms of in a lab experiment. That's easier to measure in a graduated cylinder, 36 milliliters. Right, so what is the minimum volume of magnesium chloride needed to precipitate? Right? So the volume that we must have, 36 milliliters of magnesium chloride at that concentration. So do you guys see how we're using the stoichiometry? We're using the equations that we've been found, right, recently when trying to calculate molarity. And then think about what you're given in the question. Remember, moles, odds are moles is what you're trying to find in your first step. Right? You start off with your equation, try to find the moles, and then from there try to find the moles of either one of your reactants or one of your products. Sample problem. Mercury salts have a number of important uses in industry and in chemical analysis. Because mercury compounds are poisonous, however, the mercury ions must be removed from the wastewater. Suppose that 25.00 milliliters of 0.0850 moles per liter aqueous sodium sulfide is added to 56.5 milliliters of 0.100 moles per liter of mercury 2 nitrate. What mass of mercury 2 sulfide precipitates? So if it precipitates, we know it's going to be the actual product. So let's look at the formula as we start any one of these steps. We start off with our formula, and our formula looks as such. So what we're going to do first is we're going to take the concentrations and the volume. So we've got the volume here, and make sure that we convert our volume here to liters, which is 0.00565 liters. We want to change 25 milliliters to 0.00250 liters. So now keep in mind what I've tried to do, even though it might seem like there's a lot, and I could, if I want, change the answer to scientific notation. But what I want to do is keep consistent is the number of significant digits. I have 3 significant digits in this part of the number, so I want to make sure that my conversion also has the same number of significant digits. I've got 4 significant digits here. There are my 4 significant digits. So when we're making any kind of conversion, you want to make sure you keep everything consistent. So what we're going to do is we're going to try to find the actual number of moles of our 2 reactants. And what it's asking for is what mass of mercury 2 sulfide precipitates. So what we have here, and actually I've incorrectly put in the labels. That's supposed to be aqueous. That's supposed to be our solid, because that's the mercury 2 sulfide. So what we want to do is we want to find out what is the mass of that. So to do that, what we have of each one is we've got the concentration and the volume here of aqueous sodium sulfide. So let's find the values of sodium sulfide. So we have sodium sulfide is equal to the volume, which is 0.02500 liters, times 0.085 moles per liter. When we multiply those two out, we get 0.00212 moles. So that's the number of moles for sodium sulfide. Now, let's look for the other reactant, which is the mercury 2 nitrate. And so what we have here is we've got the volume here and the concentration here of the mercury 2 nitrate. So let's do the math for here, and we get 0.0565 liters multiplied by 0.100 moles per liter, right? Liters here cancels out, and our answer is in moles, and we get 0.00565 moles. Now, what we want to do here is we want to figure out what is the limiting reactant, or what is the limiting reagent. Now, because it's a 1-to-1 ratio, and the product that we're looking at is also a 1-to-1 ratio, right? 1-to-1-to-1. What happens is we don't need to make any conversions. We don't need to make any modifications based on how many moles or how many molecules we have of each one. So because it's a 1-to-1, we take the smallest value, because it's a 1-to-1 ratio between our 2 reactants, and our product here is also to 1. So it's not really going to make any difference. So which means is the sodium sulfide is going to run out first. Which means this is the number of moles that we are going to create of mercury 2 sulfide. So the number of moles of mercury sulfide is equal to 0.00212 moles. Now, what we want to do is we want to convert those moles into grams somehow, right? So if we have moles, what do? We want to find the molar mass of mercury 2 sulfide. So what we do is we're going to take the number of moles, 0.00212 moles, and we're going to multiply it by the molar mass of the mercury 2 sulfide, which is 232.7 grams per mole. Moles cancel out. I'm left with grams. So therefore, the mass of the mercury 2 sulfide is 0.493 grams. Least number of significant digits in my question is 3, so I want to make sure that my answer also ends with 3 significant digits. Last sample problem. Silver chromate is insoluble. It forms a brick red precipitate. Calculate the mass of silver chromate that forms when 50.0 milliliters of 0.100 moles per liter silver nitrate reacts with 25.0 milliliters of 0.150 moles per liter of sodium chromate. So the first step, what we want to do is we want to come up with our equation. So here is our equation. Okay, so it's really important that you're really careful when putting together your formulas and writing out your equations. Now, what we want to do is we have information on our 2 reactants. We've got 50.0 milliliters. Okay, so we've got the volume here. We've got the concentration of silver nitrate. Using that, we can actually find the number of moles. We've got the volume here, the concentration of the sodium chromate, which is this, right? So we can use that again to find the number of moles. What we're trying to do is ultimately find that one, right? That's what we're trying to find. We're trying to find the mass of the silver chromate. So, because we've got volume and concentration, what we can do is actually use that to find the number of moles. So let's look at the number of moles of the silver nitrate. So the silver nitrate, remember, milliliters for volume, make sure you convert them to liters. Okay, that's the first step. Now, so we've got 0.00 liters, right? That's the volume. So we've converted this to this, 0.0500 liters. We're going to multiply that by the concentration, which is 0.100 moles per liter. Liters cancel out, and I'm left with 0.00500 moles. I'm going to do the same thing now for my other reactant, which is the sodium chromate. So here is my sodium chromate. I'm going to take the volume, which has been converted to 0.0250 liters. I'm going to multiply it by the concentration, which is 0.150 moles per liter. Liters cancel out, and I'm left with moles. So my answer comes out to 0.00375 moles. So that's what we have now for each one. So what we want to do is we want to figure out which one of these is the limiting reactant, or which one of these is the limiting reagent. So what I'm going to do is I'm going to erase some of this information. Okay, so we're just going to put this work aside. So let me just get rid of this, and we're going to label it on the actual equation itself, so we can actually see what these parts are actually equal to. So what did we create for the silver nitrate? So for the silver nitrate, we got 0.00500 moles. The sodium chromate, we got 0.00375 moles. So now what we want to do is we want to figure out which one is the limiting reactant. So just like we did with our stoichiometric methods, all right? Our unknown, that's the number of moles. So we want to try to find the number of moles of our unknown, and our unknown is going to be this, the silver chromate. So we've got Ag2CrO4. All right, sorry about the mess. We've got moles, we've got molecules. Now, how many molecules do we have of this unknown that we're trying to find? Well, according to our balanced equation, we have 1. So now, let's look at our first one. We have silver nitrate, and we've calculated, and just to fit it in here, 0.00, I'm going to just include the 5, and without the 2 zeros, just to fit it into my, my box here. So, we've got how many silver nitrates? Well, we've got 2 of them. And lastly, the other one that we've got is the sodium chromate. And how many moles have we created? 0.00375 moles. How many molecules do we have? Well, we have 1 of them. So what we want to do is we want to figure out the number of moles that silver nitrate is going to get of the sodium chromate. The silver chromate. And then how many moles is the sodium chromate going to make of the silver chromate? So what we're going to do, right, just as we said, separating both sides, and we've got X over 0.005 moles equals 1 over 2. So in blue we have is the silver nitrate information. In black we have the silver chromate that we're trying to find. So what we want to do is we want to isolate for X, bring the 0.05 over, and we get 0.005, right, times 1 over 2, which the answer will give me 0.00250 moles. Then we're going to do the same thing, right? X is our unknown, but this time, right? This time we're going to be comparing that ratio with the with the sodium chromate. So we've got 0.00375 moles equals 1 over 1. And anytime you have a 1-to-1 ratio, really there isn't any work to be done. 0.00375 moles. So between this and this, which has the lower number of moles that we're going to create, that will be our limiting reagent or limiting reactant. So this is our lower number of moles that we can calculate, and that was achieved from the silver nitrate. So what we're going to do is we're going to take that information and we're going to use that because we're going to create 0.0250 moles of this. So using that, right, using that information, we are actually going to be able to use that with the molar mass to help us find our actual answer. So what we're going to do, we've got our number of moles, and that's 0.00250 moles. We're going to multiply it by the molar mass, right, of this, the molar mass of that, sorry for those who can't see it, which is 331.7 grams per mole. Moles cancel out, I'm left with just grams, and when I multiply those two together, my answer comes out to 0.829 grams of the silver chromate. We were going to use